Now I want to work a series of problems that are just straightforward applications of the fundamental counting principle. This problem says an equestrian club has 15 members and wants to elect a president, vice president, and treasurer, all of whom must be different. In how many ways can this be done? Keep in mind you have 15 members and you're going to choose a president, a vice president, and a treasurer. They can't be the same person. And since being president is different than being vice president, which is different than being treasurer, the order matters. Choosing someone for president is different than choosing that same person for vice president. So it's a standard application of the fundamental accounting principle. You're going to choose a president, then you're going to choose a vice president, and then you'll choose the treasurer. There are 15 members, so any of the 15 could be chosen as president. Once you've chosen the president, you may not reuse that person and make them president and vice president, so there are only 14 left, and by the same token, you only have 13 choices for treasurer. So by the fundamental accounting principle, the answer is 15 times 14 times 13, which is 2,730. So there are 2,730 different ways that you can make a selection of president, vice president, treasurer for a club with 15 members. Okay, let's do another. This problem says how many different 3-scoop ice cream cones are possible with vanilla, peach, and berry as flavor choices. Assume that flavors may be repeated and that if the flavor appears in a different order, then that counts as a different cone. In other words, you're choosing a flavor to go first, then you're going to put another flavor on top of that, and finally you'll have the 3rd scoop. There are 3 different flavors. So for the 1st scoop, you can choose any of the 3. But it says you can repeat flavors. So that means as soon as you choose a flavor here, you can choose the same flavor again and again. So by the fundamental counting principle again, you have 3 times 3 times 3, which is 27 different ways. And it's 3 each time because you can repeat a flavor. Okay, let's do another one. A club is planning a party. They need a person to buy drinks, a different person to arrange for food, and a 3rd person to send out invitations. If the president's job is to assign each task to a different club member, and the other members are Al, Betty, Carol, Dave, Ed, Frank, and Gracie, how many ways can the president make these assignments? Again, the fundamental accounting principle applies because you're making a series of choices. You're going to choose a person to do the food. You're going to choose a person to do the drinks. And you're going to choose a person to do the invitations. You have to choose a different club member each time. So unlike the ice cream cone example, you're not going to be able to reuse a person. So there are 1, 2, 3, 4, 5, 6, 7 different people to choose from. and you can use any of them for the first choice. It doesn't matter which one you put first, but whatever you choose first, you can choose any of the 7. Once you've chosen a person, though, that person can't do a second task because it says they have to be different. So you only have 6 ways of choosing the person for the second task, and by the same analogy, 5 people we might choose to do the third task. And again, the order you write them in doesn't matter at all. You're still going to get 7 times 6 times 5, and 7 times 6 times 5 is 210. So there are 210 ways that the president could choose 3 different people to do those 3 different tasks. Okay, let's do one more. A pin tumbler lock has a series of pins, each of which must be positioned at the proper height to allow the lock to open. Inserting the proper key in the lock aligns the pins properly and allows the interior of the lock to be turned. If a pin tumbler has 4 pins, each of different lengths, how many different keys need to be tried at random to guarantee that the lock opens? Well, first of all, make sure you understand what the problem is asking. It says that each pin has 4 different heights. There are 4 pins and 4 different, I said heights, but lengths, however you want to think of it. So each pin can come to one of the 4 lengths. It can be that, just to make something up to illustrate. There are 4 different lengths. For each of the 4 positions, or for each of the 4 pins, however you want to say that. So you have 4 pins, each of which can be 4 heights. So the first pin could be one of these 4 heights. The second pin could be one of those 4 heights. The third pin could be one of those 4 heights. And the fourth pin could be one of those 4 heights. So by the fundamental counting principle, you could choose any of the 4 heights for the first pin. It could be any one of those 4. You could choose any one of those 4 heights for the second pin, any one of those 4 heights for the third pin, and any one of those 4 heights for the fourth pin. So by the fundamental counting principle, you get 4 times 4 times 4 times 4, which happens to be 256. So there are 256 ways that combination could be set to work, or how the lock combination of the pins to make the lock open. So in total there are 256 different ways. Remember, it's not 4 times 3 times 2 times 1, because these aren't things that can't be used again. These are just 4 different positions, or 4 different lengths that the pins could be.